Okay, I want to give you this lecture on where energy bands actually come from. Some of you may have a background in this. I have a feeling that many of you don't. I don't know to what depth they covered it in the physics of electrical engineering. I have a feeling maybe not too much, except to talk about the existence. I'm sure you all know about the conduction band or the valence band in a semiconductor material, at least you've heard of it. I want to give you a little bit of a sense where it comes from, so it's not just some magical thing. And you know me, I hate to just say because it's just the way it is. You know, we want to understand why everything is. Always ask why. So this lecture is going to be far more qualitative than it is quantitative. So what I want you to get out of this is more of the terminology, I'll say it that way, rather than we're not going to do any deep calculations. Indeed, the deep calculations for this subject of solid state physics could get a bit on the complicated side. I'll point you to a good reference, but we're not going to do that. Again, what I want you to know, what I want you to take away from this is terminology and hopefully get a feel of where conduction bands and valence bands come from. So there's our table of contents for this lecture. We studied quantum mechanics. We just finished that subject, and we studied the Schrodinger equation. Right? That was the new equation of mechanics that has replaced Newton's laws of motion. Newton's laws of motion still hold at a scale in which we all live, but we know that the real equation of motion is Schrodinger's equation. That could be written deceptively simple, and often is by physicists, by what's known as the Hamiltonian operator. That Hamiltonian operator is really what we derived as the Schrodinger equation. And you see why it's called an eigenvalue equation, because the Hamiltonian operator operating on the wave function psi is the energy times psi. So classic kind of eigenvalue, eigenvector, eigenfunction, I should say, equation. The phi's are the eigenfunctions, and E is the eigenvalue. And the energy E, the eigenvalue, is the total energy, the kinetic energy plus the kinetic energy plus potential energy. Of course, the kinetic energy, we know if the momentum is m times v, the mass times the velocity, the kinetic energy is 1/2 mv squared, which multiply numerator and denominator by m, then we could write the kinetic energy as p squared over 2m. In physics, they tend to describe the momentum in terms of a momentum operator. You operate on a wave function, and you get the momentum contained in that wave function with this operator, minus I h bar del. I, of course, is the square root of -1. It's really, I think, only us electrical engineers who use J. Mathematicians, physicists, and pretty much the rest of the world uses I for the square root of -1. I guess I'll probably use both, since I straddle both sides of the fence, right? So if we add the kinetic energy plus the potential energy we've just been calling it V, it's the floor of the building that we're on, right? If we write that in terms of our operator, instead of writing the p squared, we write it in terms of the operator. Lo and behold, we get the Schrodinger equation again, where this is the Schrodinger equation. This thing in parentheses here is the Hamiltonian operator, since it operates on phi. And again, you see why they call phi an eigenfunction and E an eigenvalue. Where do energy bands come from? Well, you might recall, maybe from high school, maybe from freshman chemistry, if we always look at the hydrogen atom, honestly, because it's so simple that we could solve it analytically, but it also provides a lot of information. You know, a hydrogen atom is a very simple structure. It has a nucleus, which has one proton with a charge of electron charge, but positive value, and it has an electron surrounding it, which is symmetric, usually shown in the form of an electron cloud like this. It's a very, very, very simple structure. But you know that hydrogen in nature doesn't appear as H. It appears as a molecule, H2, because hydrogen wants to bond with itself and give us the lowest energy state. So again, very qualitatively, if I have two hydrogen atoms far apart from each other, let's say this one, and I start to bring them close to each other, each hydrogen atom has a wave function. Those wave functions will start to feel the effect of each other, so they'll start to couple, and the energy band is going to split into two levels. And we want to see why that happens. Well, one of them is obviously going to be higher, and the other one is going to be lower. The higher one is called anti-bonded, and the lower one is called bonded. Of course, nature prefers the lowest energy state. And so why does this happen? Well, perhaps you remember, so with the wave functions, here are overlapping wave functions in a constructive kind of way, and here's the anti-bonded case, overlapping wave functions in a destructive interference sort of way. Perhaps you remember a single hydrogen atom, as I already said, contains one electron, which is a free valence electron, and anything that is valence 1 is highly unstable. So hydrogen has two options. It could either give up its free electron or take on a neighboring electron to fill its orbital, which in this case is 2. A full orbital would have 2 electrons, and that's a stable configuration. So by sharing 2 electrons, they form the hydrogen bond H2, which is a stable configuration, which is why hydrogen is found as not H, but H2 in nature. Okay, so even here, we already, before you even thought about things like bands and semiconductors, we see that for two simple hydrogen atoms, when they bond, when they come close together, the energy levels split into 2 levels. Well, electrons in a crystal experience a interference of wave functions as well. Why is that? Well, because again, the crystal is a nucleus surrounded by electrons, and we're going to talk for this particular topic here about the simplest kind of structure. I mean, really, crystals are 3-dimensional structures, and that starts to get complicated. But the simplest thing I could talk about is a 1-dimensional crystal, just a linear array of atoms. And if I do that, I have a periodic crystal is a periodic function, a periodic array of atoms. Well, the potential forms a periodic function, and what happens is that the energy levels, if you have n sub a atoms, they split into n sub a levels. When n atoms coupled, each atomic level of the individual atom splits into discrete levels. That splitting is really only most significant for the outermost energy bands where the wave functions interact. The inner electrons, the inner bands are shielded by the outer electrons, and so it's really just the outer electrons that matter. We know when you have 2 charges, like you do for a hydrogen atom, the Q1 and Q2, the nucleus and the electron, both have equal charge E, so it's E squared, and there's a negative sign out there because the electron is negative. This might bring back pleasant or perhaps unpleasant memories of freshman chemistry, I don't know. But if you plug this potential, this function, into Schrodinger's equation, which we had back here a moment ago, if you plug that in here, you can solve this equation for the energy eigenvalue E. I'll assume it's good news. You don't have to verify that. I'm not going to ask you to show that, but perhaps you remember the energy levels of hydrogen. It was an important result that got in chemistry, was found to be this value, E sub n. Again, the energy levels are discrete, and they start with n equal 1. That's the lowest energy state or the ground state, and as n increases, the energy levels increase by 1 over n squared, with this constant out here, m e to the 4th, and so that's all a result of the solution of Schrodinger's equation. So we'll just take this as you go look. I don't know if most freshman chemistry books do this. I don't think they do. Certainly quantum mechanics books will do it, solid state physics books will do it, but anyway, that's the result. There's the picture, right? The ground state, that famous number, minus 13.6 electron volts for n equal 1, and the energy levels going up until we get to 0. and that's what's known as the ionization level or the vacuum state. In other words, it's saying that you have to put in energy, in other words, 13.6 electron volts to take, if the hydrogen atom is in the ground state, you've got to put in this much energy. That's why it's a negative, right? You put in that much energy to take that electron and get it out of here and free it, ionize the hydrogen atom, get it to be up to 0. So an isolated hydrogen atom is characterized by discrete energy levels. No surprise for us. We will need this minus 13.6 because when we look at the doping in semiconductors, indeed a semiconductor diode laser is going to consist of doped P and N material, and to get the donor levels, I don't know if they spoke about that in physics of EE, but we'll use a trick here to obtain that. But anyway, we'll see this again, and we'll see specifically this result again. So anyway, put that aside for now. You know, the classic question that you often hear by people who don't know very little about this is that, wait a minute, if you have a positively charged nucleus and a negatively charged electron, why don't they just crash into each other? Why does the atom stay an atom? You know, why doesn't the electron? Because of the attractive force. Well, you know, there's more going on here than just the attractive force of the electron and the proton. There are also atomic forces going on. It's what gives us the characteristic size of an atom. There really is no size to an atom, but there is something that we call the Bohr radius. So for hydrogen in the ground state, this is very oversimplified, but we have our proton and that electron, if you like this picture, orbiting the electron, orbiting the proton, and the distance here is a distance r0, which is called the Bohr radius. And that's what we use to talk about the size of an atom. For hydrogen, that Bohr radius is about half an angstrom. So we say the Bohr radius for materials is on the order of 1 angstrom. So half an angstrom, 1 angstrom, 2 angstroms, they're all on the order within a factor of 10, so to speak, of 1 angstrom. So what really keeps this atom an atom is that, yes, there is a attractive Coulomb potential that wants these two things to come crashing into each other, but there are also atomic forces, atomic potentials, which are repulsive. And so these two forces fight each other, and we get a net minimum, and that's the happy minimum energy state for the potential energy. That's what defines R0 for a hydrogen atom. When two such atoms are far apart, they essentially don't see each other, right? Their energy levels remain unchanged. So hydrogen, here's a hydrogen atom. We're assuming they're far apart, and we have the energy levels E1, E2, E3, and so forth. But as they become more closely spaced, as we bring them together, the outer shell electrons, the wave functions for those outer shell electrons start to overlap and they interfere with each other. So two hydrogen atoms would split. E1 would split into E1 plus delta E and E1 minus delta E, minus delta E1, bonded and anti-bonded. Same thing for level 2, E2 plus delta E2, E2 minus delta E2. Again, why does this happen? We can go on. If we had 3 atoms, we'd split into 3 energy levels. If we had 4 atoms, we'd split into 4 energy levels. If we had N atoms, we would split into N distinct energy levels. So again, this is very qualitative, but I want to give a sense of how this happens. How could we better understand this splitting of energy levels? Well, of course, it has to be based on Schrodinger's equation. We have no clue what the wave function is for this complicated thing. This is not a simple problem. This is what's called a many-body problem, even for a linear chain of atoms like this. And it is not easy to solve, but there are some tricks we could do that'll give us some direction to show us that, yeah, this all kind of makes sense. We don't know the wave function for this. We have no idea what it might be, but one of the most powerful tools we have of your repertoire of knowledge, right, which is kind of what I want to emphasize also throughout this course. When in doubt, when you have something complicated and you have no idea how to express it whatsoever, think series, okay? Maybe Taylor series, but better yet, here, since we saw wave functions for simple quantum mechanical systems, for example, the infinite well problem, the wave functions were sines and cosines. Sines and cosines are orthogonal functions. Sines and cosines are the basis for Fourier series. So although I may not know what the actual wave function is, I could always say, well, let me try to express it as a Fourier series in terms of wave functions for the individual hydrogen atoms with some weighting function. Notice how we have the separation of variables kind of behavior here, a function of time alone and a function of space alone. Well, what I would do if I were going to solve this problem, I would substitute this wave function into Schrödinger's equation. Don't worry, we're not going to do that, but well, we are, but in a very simplified way, okay? So don't panic. So here's Schrödinger's equation once again. In other words, the Hamiltonian operator here. It's an energy operator. H operating on phi gives us the energy E times phi, where E is the total energy, kinetic plus potential. We would substitute. Don't worry too much about the don't get bogged down in details here. We would substitute our assumed series form, plug that into the Schrödinger equation, and we would get actually a linear system of equations is what this works out to. Because look, let me show you. Look at one of those equations. We have, now let's see, let me back up. I'm getting a little bit ahead of myself here. I'm going to put this assumed wave function into this that were expressed here. This is the Hamiltonian operator. I'm going to be not very mathematical and assume that it's perfectly okay to bring the operator inside. If it's a finite sum, of course, that's always the case, and I guess always a crystal is going to be a finite number of atoms, even though there might be many of them, right? So I could bring that inside. Same thing. Let's assume I could bring this time derivative operator inside the equation. And now I want to use, you remember, you've had Fourier series before. How do you find Fourier coefficients? Well, you multiply both sides of the equation. Let's say if I had phi sub j, which is what I had, I multiply both sides of the equation by some other phi sub k conjugate, and I integrate over the volume of the crystal. Only thing I'm asking you to realize, not to put in the actual functional form of the wave functions, but realize that this is an integration over a volume. It works out to be a number. This is a number, okay, whatever that number is. We'll talk about that in a minute. And what about on the other side? Well, when the wave functions for the individual atoms themselves are orthogonal. More specifically, they are orthonormal. When you do this integral, when k equals j, you get 1, and when k is not equal j, you get 0. This is standard Fourier analysis that I'm sure you've seen before. This is all I'm doing here. So this is where I got ahead of myself. In other words, I've developed a linear system of equations when I do this for all the equations, where the h's now, those numbers are a matrix. They form a matrix of values. And the w's, the weighting functions, form a vector. The elements of this matrix, of course, is just the integral that I showed you and so forth. Notice that when k equals j, you get the expected value of the energy for the original wave function. It reduces to the ordinary Schrödinger equation like the one we solved. So the diagonal terms, the jj terms of that hjk matrix, are the energy values for the unperturbed states. The off-diagonal terms, the jk terms, tell me how strong the atoms interact with each other, their coupling intensity, so to speak, the coupling strength. and that tells us something about the amount of splitting that gets experienced. You know, even if we were doing this for real, we would know exactly how to get these functions. In practice, we do not know the actual form of the wave functions or even the magnitudes of the matrix elements. Physicists or material scientists would do this experimentally to get those values. And the mouse is jumping on me. Let's look at a simple example. What's the simplest example we could imagine? What's the simplest crystal you could possibly think of? 2 atoms, 2 simple atoms like this. So this system of equations reduces to basically 2 equations, 2 unknowns. And since these 2 atoms, I'm assuming, are identical, H11 and H22 is E1. Similarly, the way atom 2 interacts with atom 1 is the same as the way atom 1 interacts with atom 2. So it's reasonable to say that H12 equals H21, and I'll call that delta E, okay, because it's an interaction strength. So to find the energy of the coupled system, I simply do what we've always done. I assume a plane wave, a constant, times e to the minus j omega t. I substitute that into this system of 2 equations here. Okay, very simple. Substitute this. And I solve these equations for the constants C1 and C2, the constants I'm looking for. What I get is that, when I solve them, is that C1 squared equals C2 squared. In other words, C1 equals plus or minus C2. If you want to see the math, there's the math for those of you. There's the substitution into the 2x2 system of equations. Here's the math for me solving for the constants C1 and C2. It's not complicated. Okay? So for C1 equals C2, then what? E equals E1 plus delta E. For C1 equal minus C2, E equals E1 minus delta E. So lo and behold, the original single energy level E1 for the isolated atoms has split into 2 energy levels, E1 plus delta E, E1 minus delta E. N sub A atoms would lead to N sub A symmetrically spaced energy levels about E1. Okay. I've convinced you, I hope, qualitatively, and a little more than qualitatively, I've convinced you, I hope, that energy levels split, but how are bands formed? How do you get things like a conduction band and a valence band? I want to show you that now. Consider again a simple one-dimensional crystal. It's as simple as we could make it. Right here's a one-dimensional crystal of atoms. This is the many-body problem that I spoke about. That's in principle very difficult to solve. But let me do the following. Let me just assume these atoms are all their wave functions. Each one is going to have a wave function. They're all going to interact with each other to form one big composite wave function for this crystal. Okay, that's what gets complicated. Let me make an assumption that I only have to worry about coupling between nearest neighbors. So for example, pick this atom right here. This one only feels the presence of this one, not this one, okay, or this one. Right? And similarly, this one also only feels the presence of this one, but not this one. If I do that, if I just assume a nearest neighbor approximation, I could simplify this tremendously, and lo and behold, we're going to see energy bands are formed even for this simple one-dimensional crystal with only nearest neighbor interactions. Again, how would I do it? Same kind of approach. I would take HKK, let's say, to be energy E1, and then HJK to be delta E. So I take my system of equations from before, and here I only have, I take out a representative atom, right? The kth atom, okay? Its value of energy is HKK. And on this side, I have HK plus 1 for delta energy. On this one, I have HK minus 1 for delta energy. So I have E1 for HKK, and again I assume that the minus 1 and plus 1 terms both have, since they're identical atoms and nearest neighbors, I have delta E. Notice what I've generated for myself here is a difference equation now. You know how to solve difference equations, right? You've done those in signals and systems probably, or places like that. What do you do? let's see a little bit more clearly that it is a difference equation. I take my usual for W of t, my sinusoidal steady state. You should recognize now that this is a constant c sub j times e to the minus j omega t. I substitute that into my original equation. I substitute that into my original equation for the w's here. When I do that and do the cancellations and so forth, that's what I'm left with. And again, lo and behold, I get these coefficients. I got to find these coefficients. They form a difference equation. In other words, C sub k is for lattice position x sub k, atom k, and on either side I have one of them k plus 1, the other one k minus 1. They're going to be periodic, and the lattice spacing is a. So this is a difference equation where the C sub k's follow this sort of the second order difference equation. How do you solve a second order difference equation? Again, you do it much the same way you solve a differential equation. Once again, you assume an exponential solution of this form. Again, somewhere in your background you've seen the solution to difference equations, most certainly, because we live in a digital world, right? So we again do the math. I substitute into that. Here's my math. I leave nothing to your imagination. You could check all my steps. Lo and behold, look what I get. I get that E is equal to E1 plus 2 delta E cosine Ka. Draw a picture of that for yourself. What's happened is that linear chain of atoms with nearest neighbor coupling gave me for the energy not discrete values. It's not a discrete value anymore. It's a band. It's a band characterized by a central energy of E1 and a variation around it of 2 delta E cosine Ka. So here is an allowed band of energy. It's a forbidden region up here and a forbidden region down here. So in an infinite one-dimensional crystal, a continuum of energy between E1 plus or minus 2 delta E is allowed. This is the energy band that we're talking to. Now, this was for an infinite crystal. No crystal is infinite. The world isn't big enough. The universe isn't big enough to hold an infinite crystal. Crystals, of course, are finite in size. In fact, they're tiny in most semiconductor applications. For finite crystals, these energy levels are not going to be continuous, as I found here with a cosine for an infinitely long crystal. They're going to be finite, but they're going to be so closely spaced that for all, and we're going to see that, for all intents and purposes, we could treat them as though they were a continuous variable. So these bands occur for all higher lying electron energy levels when the atoms are bonded together to form crystals. The next higher band is going to do the same kind of thing. E2 is also going to split. E3 is going to split and so forth. E2 is going to split, we'll call it E prime, is going to be E2 plus delta E prime cosine Ka. There are two ways this can happen that what we're going to be starting to see here. There are semiconductors called direct bandgap semiconductors and indirect bandgap semiconductors. For direct bandgap semiconductors, the sign for the next band is going to be reversed. This is going to become a minus. Let me show you a picture. There's actually here what I just said. This is very important, extremely important, as a matter of fact. This is something I could most certainly ask you and expect you to have on the tip of your fingers. For a direct bandgap semiconductors, the conduction band minimum occurs at the same K value as does the valence band maximum, like this. And the distance separating them is called the band gap. Gallium arsenide is an example of a direct bandgap semiconductor. Once again, the minimum of the conduction band and the maximum of the valence band coincide for the same value of K. That's going to make the transition of an electron from here to here very easy, and that's going to easily produce a photon for us. We'll talk more about this later. There are other materials that are called indirect bandgap semiconductors, and that is where the minimum of the conduction band and the maximum of the valence band, although there's still a gap, they do not coincide. Silicon is an example of an indirect band gap semiconductor. We find it is very difficult to make a transition from the bottom of the valence band to the top of the conduction band, and we'll see why that is a little bit later. It's why you tend not to see silicon or germanium lasers. People are trying so hard. I mean, silicon. Go to the beach. Sand is silicon, right? It's all over the world. It's cheap. We know how to refine it to incredible levels of purity and grow crystals and so forth, but it's got a problem when it comes to optoelectronic applications. Gallium arsenide is a far more cooperative material. If you don't fully appreciate that now, I don't expect you to. Hang on, as we're going to move on, this is going to start to make more sense. Some more terminology. As I said, the purpose of this lecture is really one of terminology more than anything else. We found these are cosine functions, right? A periodic function. If it's a periodic function, all you need to know is one period. And if the spacing of the atoms is A, the spacing between these guys is going to be 2 pi over A. I'll say more about that later too. But if it's a periodic function, all I need to know is one period. If I have one period, I have everything. And that period is given the name of a Brillouin zone. So for our one-dimensional crystal where our lattice ran along the x direction, the band functions we saw looked like cosines, right? Well, here they are. I'm drawing it for the case of a direct band gap material. But again, since it's cosine and it's periodic, I only need to know one period, and that one period is called a Brillouin zone. For real things are three-dimensional. We're not going to do that again. It's okay, right? For real three-dimensional crystals with lattice constants, not just AA, but now A, B, and D. They don't have to be the same in the three directions, right? The spacing, for example, along the x direction could be A, half an angstrom or something. It could be a different number along the y direction and yet a different number D along the z direction. If you were to do a similar procedure, we won't, again, but if you were to do a similar procedure, instead of just E plus delta E, you'd have E sub x and delta E sub x and delta E sub y and delta E sub z. You would assume a W of the form of a plane wave. There's our plane wave, and I'm using J again for the spirit of -1, and e to the minus j omega t. What you would find is E splits into E1 plus 2 delta EX cosine k sub x times A, plus 2 delta EY cosine k sub y times B, 2 delta EZ cosine k sub z times D. So we get the equivalent three-dimensional structure. For semiconductor materials, if they're at 0 degrees Kelvin, absolute zero, all of the states of all bands up to and including the valence band are full. Important, in a semiconductor, at 0 degrees Kelvin, all the states are filled in all the bands up to and including the valence band. Okay? The valence band is full for a semiconductor at 0 degrees Kelvin. The next higher band is called the conduction band, and that is empty. Okay? So the potentials affecting electrons in such semiconductors are, of course, more complicated than what we've been doing here. But as a result of that, the EK plots are not perfect sine waves. I'll show you in a picture for a minute. I think I've got an extra slide in here. Did I go in the wrong direction? No, I put an extra slide in here. Here's again a qualitative picture. If we look at for this formation of any energy bands, if we look at individual atoms, and here's the atomic spacing. Okay, if the atoms are very far apart from each other, okay, so one atom is very far away from its neighboring atom, right? The energy levels are discrete. And of course there could be more bands up here. Those bands are going to be empty. Okay? As the spacing between the atoms gets closer and closer, now this is a PowerPoint cartoon on my part, but you could find this picture in any number of places, the energy levels start to split, as we've seen. Okay? When we get to the typical, for example, gallium arsenide, the atomic spacings are anywhere from 3 to 7 angstroms. Go in the middle. 5 angstroms, 3 to 7, 5 is in the middle, right? For a 5 angstrom spacing, like you typically find for gallium arsenide, this is what the splitting functions would look like. You would have a band with a gap, right, as we've seen, and then a band, and then a gap, and then a band, and then a gap. So we have an allowed energy band, an energy gap, an allowed energy band, and an energy gap, an allowed energy band, and an energy gap, and so forth. Okay? This is typically what all materials do. Once again, very important. The highest energy band that is completely filled is called the valence band at 0 degrees Kelvin. The next higher band is called the conduction band, and these bands are separated by a band gap. Okay, that much I expect you to know. I'm going to stop here because I'm going to continue with a part 2. We've been going for 36 minutes, and that's enough for one chunk. And I want to talk about what happens when the energy wells that we're talking about become so small that I could see the detail of the atomic spacing in there. That's a very important case because pretty much every laser today has this, what's known as a quantum well structure, where the spacing is very, very small, and we can neglect the fact that we have these. We could see there might only be a dozen or so atoms in a well. That's what where we're at today. So anyway, let me stop, and we'll come back to this in a moment.